Okay, stats. 8.2 is extremely similar to 8.1, except it's about population proportions and sample proportions instead of actual measurements. So in the past, in the last video, if we told you that, like say the systolic blood pressure had a certain mean and standard deviation, the larger the sample of ladies was, the smaller the standard deviation of their blood pressure, the mean of their blood pressures was. The same thing happens here. It's a sample proportion. So if someone told you something like 40% of households have 3 cars, or 0.4 as a probability, if you took a sample of, say, 10 houses, you could expect a pretty wide range of how many you would find have 3 cars. There's only 10 houses. But as you got a larger and larger group, you should get closer and closer on average, or less deviation, and it should approach 0.4 more easily. So to reiterate, a point estimate of a population proportion, suppose a random sample of size n is obtained from a population in which each individual either does or doesn't have something, and they have 3 cars or they don't. The sample proportion, which will look like p with a little hat on it, is given by x divided by n, where x is the number of successes for that characteristic and n is the total number of observations. The sample proportion is a statistic that estimates the population proportion. So in a random sample of 500 households, 180 own a dog, find the sample proportion. We just need to take 180 divided by 500, which is 0.36. Now again, this estimate should always be between 0 and 1. 0 meaning no one ever had anything, 1 meaning everyone has the characteristic. Now, if you took another sample, will you get the exact same proportion? Probably not. So it's just like our means. If we do a bunch of different random samples of the population, eventually we should have some probability distributions associated with them, and then their averages can be used to find the shape of a distribution overall, and it'll make the means and standard deviations a little easier to calculate. But our standard deviations should get smaller the more samples we have. So for a simple random sample of size n with population proportion p, the shape of the sampling distribution p hat, so if this isn't normal, we know a way to make it normal, or check if it's approximately normal, and that's if n times p times 1 minus p is greater than or equal to 10. This should look familiar because we've used that formula before, probably way back in chapters 1, 2, or 3, I think. Now the mean of the sampling distribution p hat is just p. So if someone tells you that there's a 40% chance that the household owns a dog, you expect in your population, like when you're doing your sample, to get about 40% of the population, or 0.4 as a proportion, should have a dog. Standard deviation for p hat is the square root of p times 1 minus p over n. This should look similar to the binomial distribution, where you have to divide by n again because you're doing proportion. Now, if you divide the square root of n times p times 1 minus p overall divided by n, it ends up that you've got a square root of n in the denominator. That's probably how powers work. So let's do some actual problems. There's not too many because they're similar. According to the American Veterinary Medical Association, 37% of the U.S. households own a dog. Suppose a random sample of 500 households are asked, do you own a dog? Describe the sampling distribution and the proportion of households that own a dog. Okay, so we need, in order for this to be normal, n times p times 1 minus p needs to be greater than or equal to 10. Now the number of households in this sample are 500. The expected number that own a dog should be 0.37, because this is 37%. And that means 1 minus 0.37 is our 1 minus p. This is actually 0.63, but you can put it in just like this. Is that greater than or equal to 10? Well, if you multiply these 3 together, it ends up being about 100 and something. So it is way bigger than 10. But you can multiply it out yourself just to get used to putting this in the calculator. But I promise it's way bigger. We're totally fine here. It should be approximately normal. So my average should be the same as my average previously, which which was the 0.37. My standard deviation, though, it says I need to take the square root of that 0.37, which is p, and my 1 minus p, which is 0.63, and divide it by 500. This is approximately 0.022. So what does that mean? That means if I ask 500 households, I should expect about 0.37 to have a dog. And my standard deviation is only 0.022. So that means every standard deviation in either direction should be 0.02 to roughly a little more than 0.02 away on each side. So if I subtract 0.02, one standard deviation below is about 0.35. One standard deviation above would be about 0.39. So it doesn't vary a lot in the population proportion because my sample size is so big at 500. So what can we do with this information? According to the Centers for Disease Control and Prevention, 18.8% of school-aged children aged 6 to 11 years were overweight in 2004. If a random sample of 90 school-aged children aged 6 to 11 years is taken, then what is the probability that at least 19% are overweight? So first, let's check if it's normal. Again, n times p times 1 minus p, so that's 90. My p looks like it's 0.188. My 1 minus 0.188, or this is 0.812. If I multiply those all together, I get 13.74. Is that bigger than or equal to 10? Yes, so it's approximately normal. What's my average? My sample, my expected value for the sample proportion, it should be that same one as the original, the 0.188. So let me draw a line under this. This thing should still be 0.188. But my standard deviation, I need to use this. So that's 0.188 times that 0.812, all under the square root, divided by my sample size, which is 90, which is 0.041. So now I have a sample mean and a sample standard deviation, so let's look at the z-score. My actual amount of kids, I know I'm looking for 19%, so that'd be 0.19 as a decimal minus 0.188 over 0.041, which is approximately 0.05. So we're looking for the area above 0.05. Here. So it says find the area to the right. So let's start by finding the area to the left, because that's what our table will give us. If we look at 0.05, so that's 0.0 on the left and the 0.05 on the top, we get 0.5199. So if I do the area to the right, I need to do 1 minus 0.5199, because this gives me the area to the left. So it's 0.4801. So it's saying there's about a 48% chance we would have at least 19% students. It's not that unusual. Now, suppose a random sample of 90 school-aged children aged 6 to 11 years results in 24 or more overweight children. What might you conclude? Well, we need a population proportion, so I need to take my 24 over 90, and that gives me 0.267. Now, what's the z-score here? 0.267 minus 0.188, so it's the same one from our sample above, which is, if you divide it, 1.93. 1.93 is, so if we look at our table, 1.93, it's asking yourself, let's look at our thing, we're looking for what 1.93 is here, to the right. So if we look at 1.93 on the table, we find a decimal, this is about 0.0, so the decimal to the left of 1.93 is about 0.03. It's not exactly, what's 0.97. Getting ahead of myself. So what's 1 minus 0.97? 0.03. So is it unusual? It looks like yes, because it has a less than 5%